Hi, we continue chapter 1 and we would like to solve this example. We need to prove for each sequence that it's convergent and we need to determine its limit. So let's take the first one. Un equal cosine n over n. The first idea that comes into mind is to try to investigate the fact that cosine n is bounded. So we have two ways to think. Whether we can say that cosine n is bounded and it's multiplied by 1 over n, which is a sequence that goes to 0, which means that the whole sequence un is going to 0 because it's convergent and it goes to 0 because of the theorem that we already did in the course that says that a bounded sequence times a sequence that goes to 0, the product goes to 0. Or we can think through the sandwich theorem. So with the sandwich theorem, we can say that we know that we have cosine n is always between -1 and 1, right? Then if you multiply it by 1 over n, then cosine n over n, because it's positive, we can multiply by 1 over n because it's positive, it's between 1 over n and -1 over n. Okay, then this is true, of course, for all n and n star. Then we have the sequence in here that goes to 0 when n tends to infinity, and the one in here, it goes to 0 when n tends to infinity. Therefore, from the sandwich theorem, un is convergent and limit of un when n tends to plus infinity is equal to 0. For the second example, we have un is equal to the sum k going from 1 to n of 1 over square root of n squared plus 2k. So to think in here, we need to find an upper bound and a lower bound of this sequence. Let's take for example the strategy that says that a sum is always less than the number of its elements times the highest or the greatest term, and is greater than the number of its elements times the least term. So it gives that the sum un is between the greatest term in here is the first one, because it's for k equal 1, it's for the least denominator. So the lowest term of the sum is 1 over square root of n squared plus 2, and we multiply it by the number of terms. K going from 1 to n means that we have n terms, and is greater, un is greater than 1 over the least term, which is square root of n2 plus 2n times the number of elements, which is n. So again, 1 over n2 plus 2 is the greatest term, square root of n2 plus 2, of course, times number of terms, which is n, and 1 over square root n2 plus 2n is the least term times n, which is the number of terms. So on the right side, we have n over square root of n squared plus 2, which is equal to n over n square root of 1 plus 2 over n squared. So if we simplify n by n, this is something that goes to 1 when n tends to plus infinity. And on the left side, it's the same thing. We have n over square root of n squared plus 2n, which is equal to n over n square root of 1 plus 2 over n, which is something that goes to 1 when n tends to plus infinity. So we have both sides that goes to 1. Then from the sandwich theorem, UN is convergent and limit of UN when n tends to plus infinity, of course, is equal to 1. Now taking the third example, it's the sum k going from 1 to n squared of 1 over square root of n squared plus 2k. If we compare visually this example with the one we did right before, we can notice that the sum of the terms in there goes to n, while here it goes to n squared. The difference is that when we will multiply by the number of terms, we will be multiplying by n squared and not by n, which will give an additional degree to the numerator, which might go to infinity and not to a constant. So it will lead the fraction to go to infinity and not to a constant. Okay, so we'll try to do it. Let's try to find a lower bound first. We know that un is greater than the least term, which is 1 over square root of n squared plus 2n squared, times the number of terms, which is n squared. So here you have the least term, and here we have the number of terms. So this is equal to n squared over square root of n squared plus, or even, it's 3n squared. So which is equal to n over, or n squared over n radical 3, which is n over radical 3. And this term, it goes to plus infinity when n tends to plus infinity. So we proved that un is greater than something that goes to plus infinity. So it doesn't make sense now to find an upper bound of un, because it's clear that if un is greater than a sequence going to plus infinity, then un itself is going to plus infinity. Then un goes to plus infinity when n tends to plus infinity. Now for the last example, we have un equal to 1 over n3 sum k going from 1 to 3, to n, of k e of kx. Okay, so we need to find an upper bound and a lower bound to this thing. Of course, we know already that e of x is something that is bounded by x from the right side and by x minus 1 from the left side. Of course, it can be equal to x if x is an integer. So if we take this, we can say that it means that e of kx is bounded between kx from one side and kx minus 1 from the other side. So apply this to the formula that we have. It means that sum of k e of kx, k going from 1 to n in here, is between sum k going from 1 to n of k times kx on one side, and from the other side it's sum k going from 1 to n of k times kx minus 1. We can of course multiply all the terms by 1 over n3 to obtain un. So 1 over n3, 1 over n3, and 1 over n3, and this way we have un in here. Okay, so this means that un is, from the right side, is less than x over n3 sum k going from 1 to n of k squared, and on the left side it's 1 x over n3, sum k going from 1 to n of k squared minus 1 over n3 sum k going from 1 to n of k. Now sum 1 going from 1 to n of k, this is something you can easily determine because it's the sum of an arithmetic sequence of first term 1 of common difference 1. And you have the sum from the first term to the nth term. So it means that it's the first term plus the last term times the number of terms over 2. But what about the sum for k of k squared when k is equal to 1? This is a separate exercise that you can try to do yourself. So prove that, or prove by induction, that sum k going from 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 over 6. So try to prove this by induction. So here the sum of n squared is equal to n times n plus 1 times 2n plus 1 over 6. So we replace everybody. We will have un less than, on the right side we will have x over let's say 6n squared, and in the numerator we have n plus 1 and 2n plus 1, while on the left side we will have x times n plus 1 2n plus 1 over 6n for the first term minus 1 plus n over 2n squared for the second term. It's of course 6n squared in here. So now we have this term that goes to, when n tends to plus infinity, we have a polynomial of or not a degree of n squared in the numerator, a degree of n squared in the denominator. So the limit would be x times 2 over 6, which will give x over 3. And on the left side, this is something that goes as well to x over 3 when n tends to plus infinity. And this is something that goes to 0 when n tends to plus infinity, because we have a degree of n squared in the denominator and a degree of 1 in the numerator. So we have on both sides sequences that goes to x over 3, then un converge, and limit of un is x over 3 when n tends to plus infinity. Of course, it's the sandwich theorem.